You are welcome to the Physics Hub as we continue our studies on circular motion. Today we're dealing with part 2 of the series, and it involves solving problems involving a uniform horizontal circular motion. So I expect you by the end of today's class that you should be able to solve problems involving horizontal circular motion only in the context of tangential velocity and speed along the circular path. Right. Those who watched or attended the first class when we were introducing circular motion, we talked about some key parameters, some key properties observed by an object moving in a circular path. Number one, we said the radius will remain constant. As the object is moving around the circle, the radius does not change. So in this case, the radius will be 1.2 throughout the course of the movement. And we also say the speed is constant. Speed is constant. It's not changing, though velocity is constantly changing. Why? You may have to watch part 1 for you to get those explanations. Number 2, we said tangential velocity, the one we want to use today to solve problems, is perpendicular. It's at right angles to the radius of the circular path. So this is our tangential velocity. We discussed it in part 1. Now I want you to see that in a circular path, the weight of the object and the tension which provides for the centripetal force, we talked about it in part 1, is always perpendicular to the radius of the circle. The weight and the radius are perpendicular, and our centripetal force is along the radius. So these two are perpendicular. Lastly, I want you to realize that the gravitational potential energy of the object remains the same. In other words, the height of the object from the ground does not change since it is a horizontal circle. Now, in today's business, we want to calculate the centripetal force using tangential velocity, which in magnitude is the same as the speed along the circular path. We want to find the relationship between centripetal force and tangential velocity, which is the same as the speed along the circular path. So how do we calculate centripetal acceleration and centripetal force with respect to tangential speed? When I'm saying tangential speed, I'm talking about the speed along the circular path. Now, we define the centripetal acceleration as the acceleration experienced by an object moving in a circular path. And we said it is always directed towards the center. How do we calculate it? This is the relationship you need if you are doing A2 physics. The centripetal acceleration of an object is equal to the square of the velocity divided by the radius. This is the expression I'm going to call equation number 1, the one we use to solve for centripetal acceleration. It relates centripetal acceleration to the radius and to the speed. Which speed? Tangential speed, the speed along a circular path. In our next class, part 3, we'll be talking about angular speed. There are two speeds involved in circular motion. We have tangential speed, tangential velocity, the speed along the circular path, and we have angular speed. That's the business for the next class. Now, how do we calculate centripetal force? Newton said F is equals to ma. Whenever there is an acceleration, there must be a force responsible for that acceleration. Now, if our A is the same as v squared over r, we can safely say, according to Newton, the centripetal force is mv squared over r. Taking the expression for centripetal acceleration and plugging it into Newton's second law. So we end up coming up with an expression which says the centripetal force is equal to mv squared over r, just derived from Newton's second law, F is equals to ma. We know that our A is the same as v squared over r, so substituting, we are going to say mv squared over r. Remember, the centripetal force is a key force. It's that all-important force in circular motion because it keeps the object in a circular path. That was covered in part 1 when we're introducing circular motion. Now let me give you a typical exam question which will be solved using this equation. Here is an example. A small rubber stopper is swung in a horizontal circle as shown below. This is your diagram. Explain what happens to the tension in the string if the rubber stopper is spun faster without changing the radius of the circle. In uniform circular motion, the radius must remain the same. Now, there are some things we need to understand. Number one, mass is constant. Why are we saying mass is constant? It's the same rubber stopper. It's the same rubber stopper. We're still using the same object, so mass remained constant. Number two, radius remains constant. Why? The question says without changing the radius of the circle. So how are we going to answer this question? You will see that if the speed is increased, the tension will increase. And if it exceeds the limit of the string will break. You will talk about this under deformation. If the speed is increased without changing the radius, without changing the mass, the tension will increase. And if the tension increases to a level beyond the limit the string can take, the string will break. Now, this could be one mark out of these three. The question is saying, explain your answer. That's where the other 2 marks are going to come in. Now, how do we justify this statement here that the tension is going to increase if the speed is increased? We need to revisit the equation which calculates centripetal force. Why? The tension in the string here is provided by, it's actually the centripetal force. So our tension is the centripetal force. The centripetal force is provided by the tension. Now, if mass is constant, radius is constant, we can say m over r is equal to k, a constant of proportionality. Therefore, this equation can be reduced to Fc is directly proportional to v squared, where we can safely say Fc is equals to k v squared, where our constant of proportionality is mass over velocity. Now, with this relationship, we can say the centripetal force is directly proportional to the square of the velocity. What is directly proportional? What does this mean? As one is getting bigger, the other one is getting bigger. So when we're talking about direct proportionality, we're talking about something which looks like this. As the V is getting smaller, F is also responding in the same way. It's getting smaller. As the V is getting bigger from right to left, F will be getting bigger from right to left. So we can safely say the centripetal force, which is the tension, is directly proportional to the square of the velocity. Hence, if you increase the velocity, we expect the tension to increase. But can it keep increasing forever? Deformation does not allow that. It says if it exceeds the limit the string can bear, then the string will break. Right, let me give another example which involves calculations using this equation. A small object of mass 0.2 kilograms is attached to a string and swung in a horizontal circle of radius 2 meters. If the object moves with a speed of 6 meters per second, determine the centripetal acceleration experienced by the object, the centripetal force exerted by the string. Now, let's collect data. We are given the radius, which is 2 meters. We are given the speed, which is 6 meters per second. We are given the mass, which is 2 kilograms. We want to calculate the centripetal acceleration. We have agreed that centripetal acceleration is equal to v squared over r. We recall that equation to solve part A. Centripetal acceleration is v squared divided by r. Let's put numbers for letters. What is the v? 6. We square the velocity. What is the radius? 2 meters. What are we going to get? We're going to get 18 meters per square second. Now, part B says the centripetal force exerted by the string. And we said, according to Newton, F net is equals to ma. So we just need to multiply our centripetal acceleration with the mass of the object. That brings us to the second equation, which says centripetal force is mv squared over r. Let's substitute. M is 0.2 kilograms, v is 6, we square it, divided by 2, the radius. We are going to get a force of 3.6 newtons. Let's take a break, and during the break, attempt to solve example 2. Once we come back from the break, I'm going to provide the solution and you mark yourself. You are welcome. Now let's get into the solution to this question. A car of mass 1,200 kilograms travels around a horizontal track with a radius of 50 meters at a constant speed of 20 meters per second. Calculate the centripetal force acting upon the car. And part B requires us to calculate the centripetal acceleration experienced by the car. This is the opposite to the question we're just from doing. So let's collect data. We are given the radius 50. We are given the speed 20 meters per second. We are given the mass of the car. And for us to find centripetal acceleration, we have already said Fc is mv squared over r. You need this equation if you are doing A2. Very, very important equation. Now, let's recall our equation and put substitution. Mass is 1,200. Speed is 20. We square it, divided by 50, which is the radius. And you are going to get 9,600 newtons. I hope you managed to get all the marks right. Part B, without wasting time, we are looking for the centripetal acceleration. We can go for AC is v squared over r by dividing by m from Newton's second law. So we recall our equation for centripetal acceleration, v squared over r. We square the velocity 20 squared divided by 50, the radius, and we will get 8 meters per square second. With this, I'll leave you with these 3 practice questions. Enjoy your studies. Signing out is your senior coach, Chigo. See you for part 3.